Subscribe so you don't miss out on any of these videos. The mysteries of the cosmos have intrigued humanity for millennia. Staring into the vastness of space, people have always wondered about the secrets that lie beyond our atmosphere, the invisible forces shaping the universe, and our place in this grand expanse. Even with modern science and powerful technology, the universe remains full of enigmas that challenge our understanding. The cosmos, a realm of stars, galaxies, and black holes, unfolds like a deep, infinite puzzle, with each discovery often leading to more questions than answers. Our fascination with the stars began in ancient times when humans first observed the night sky. Early civilizations charted the movements of celestial bodies and used them to mark seasons, navigate oceans, and predict events. Yet, as our knowledge expanded, it became clear that the stars were not eternal or fixed. Instead, they were part of a much larger, dynamic universe in which entire galaxies could be born, live, and die in cosmic time scales. At the heart of this ongoing quest to understand the cosmos is one fundamental question: how did the universe begin? The Big Bang Theory, proposed in the 20th century, is the leading explanation for the origin of the universe. According to this theory, around 13.8 billion years ago, the universe began as a singularity, an infinitely dense point, and rapidly expanded. This expansion, which continues to this day, created all matter, energy, and space itself. The evidence supporting the Big Bang includes the cosmic microwave background radiation, the afterglow of the universe's early state, and the observable redshift of galaxies moving away from us, suggesting that the universe is still expanding. However, the Big Bang Theory does not explain everything. For instance, what caused the singularity to exist in the first place? What was there before the Big Bang? Some theories suggest a cyclical model, where the universe undergoes infinite cycles of expansion and contraction, while others propose the existence of a multiverse, a collection of parallel universes, each with its own set of physical laws. Yet, these ideas remain speculative and far from conclusive, raising the possibility that we may never fully comprehend the true origins of the universe. Another profound mystery of the cosmos is the nature of dark matter and dark energy. Together, these two enigmatic substances make up about 95% of the universe, yet they remain elusive and largely undetectable. Dark matter, first proposed to explain the gravitational effects observed in galaxies, is believed to be a form of matter that does not emit, absorb, or reflect light. Its presence is inferred from its gravitational influence on visible matter, such as stars and galaxies. Without dark matter, galaxies would not hold together, and their rotation speeds would not match the observed data. But despite decades of research, no one has been able to directly detect dark matter particles. Dark energy, on the other hand, is even more mysterious. It is thought to be responsible for the accelerated expansion of the universe, a discovery that shook the scientific community in the late 1990s. Before this revelation, scientists assumed that gravity would eventually slow down the expansion of the universe. Instead, dark energy appears to act as a repulsive force, pushing galaxies apart at an ever-increasing rate. The true nature of dark energy is still unknown, and its discovery has led to new questions about the ultimate fate of the universe. Will the universe continue to expand forever, growing colder and more desolate? Or will it one day reverse course, leading to a catastrophic collapse known as the Big Crunch? Black holes are another cosmic mystery that continues to baffle scientists. First predicted by Albert Einstein's general theory of relativity, black holes are regions of spacetime where gravity is so intense that nothing, not even light, can escape. They are formed when massive stars exhaust their nuclear fuel and collapse under their own gravity. At the core of a black hole lies a singularity, a point of infinite density where the laws of physics, as we know them, break down. Surrounding this singularity is the event horizon, the point of no return. Once something crosses this threshold, it is forever trapped inside the black hole. Despite their seemingly destructive nature, black holes may play a crucial role in the formation and evolution of galaxies. Supermassive black holes, which are millions to billions of times more massive than our Sun, reside at the centers of most galaxies, including our own Milky Way. These black holes influence the orbits of stars and gas clouds, and their powerful jets of energy can shape entire galaxies. But what happens inside a black hole remains one of the greatest mysteries in astrophysics. Some theories suggest that black holes could serve as gateways to other regions of spacetime, or even parallel universes, though these ideas are purely speculative at this point. Beyond the mysteries of black holes and dark matter, there are more mind-bending questions about the very structure of the universe. One such question is the nature of time. We experience time as a linear progression from the past to the future, but in the context of Einstein's theory of relativity, time is not a constant. Time can be stretched or compressed depending on the observer's speed and position in a gravitational field. This means that time flows differently for someone near a massive object, like a black hole, compared to someone far away. Could time itself be an illusion, a construct of our limited perception? Some physicists argue that the past, present, and future all exist simultaneously in a block universe, where time is just another dimension, like space. Another enigma is the fine-tuning of the universe. The fundamental physical constants that govern the universe, such as the strength of gravity or the charge of the electron, appear to be finely tuned for the existence of life. If any of these constants were slightly different, stars might not form, atoms might not hold together, and life as we know it would be impossible. This has led some to wonder whether the universe was designed with life in mind, while others suggest that the fine-tuning could be explained by the multiverse hypothesis. In this scenario, our universe is just one of many, each with its own set of physical laws. We happen to live in a universe where the conditions are right for life, but countless other universes may exist where life is impossible. While the search for extraterrestrial life has yet to yield definitive results, it remains one of the most tantalizing questions in the study of the cosmos. The sheer size of the universe, with its billions of galaxies and trillions of stars, suggests that life could exist elsewhere. The discovery of exoplanets, planets orbiting stars outside our solar system, has only fueled this speculation. Some exoplanets are located in the habitable zone of their stars, where conditions might be suitable for liquid water and potentially life. Yet, despite extensive searches for signals from intelligent civilizations, we have found no conclusive evidence that we are not alone. This brings us to the Fermi paradox, a famous contradiction named after the physicist Enrico Fermi. Given the vast number of stars and planets in the galaxy, many of which are older than our solar system, why haven't we encountered evidence of advanced extraterrestrial civilizations? Various explanations have been proposed, ranging from the idea that intelligent civilizations are rare or short-lived, to the possibility that they deliberately avoid contact with us. Some even suggest that we are living in a cosmic zoo, where advanced civilizations observe us from a distance but do not interfere. The mysteries of the cosmos are not limited to the distant reaches of space. They also extend to the fundamental particles that make up matter. Quantum mechanics, the branch of physics that deals with particles at the smallest scales, reveals a universe that is profoundly different from our everyday experience. At the quantum level, particles can exist in multiple states at once, can be entangled across vast distances, and can behave in ways that seem to defy logic. The famous double-slit experiment, for example, shows that particles of light, photons, can behave both as particles and waves, depending on how they are observed. This leads to a perplexing question. Does the act of observation affect reality itself? Some interpretations of quantum mechanics suggest that consciousness plays a role in determining the outcome of events at the quantum level. This idea, known as the observer effect, has led to philosophical debates about the nature of reality and whether the universe exists independently of our observation. Could the mysteries of the cosmos ultimately be tied to the mysteries of consciousness? Or is there a deeper layer of reality that we have yet to uncover? The interplay between quantum mechanics and the nature of reality raises profound questions about the fabric of the cosmos. If the act of observation can affect quantum events, this suggests a universe that is far more complex than we had imagined, a universe that might be participatory in some fundamental way. The idea that consciousness could influence reality may seem like science fiction, but it has led to serious debates among physicists and philosophers alike. Some suggest that the universe and consciousness are intimately connected, perhaps even inseparable, while others believe that these quantum oddities only apply at the smallest scales and have no bearing on the larger, classical universe. One of the most puzzling aspects of quantum mechanics is quantum entanglement, a phenomenon in which two or more particles become so deeply connected that the state of one particle instantaneously affects the state of the other, regardless of the distance between them. This spooky action at a distance, as Einstein famously called it, has been experimentally verified, but its implications remain mind-boggling. How can information travel faster than the speed of light, seemingly violating the laws of physics? Does this suggest that space and time, as we understand them, are not the fundamental fabric of reality? Some theories propose that entanglement could be a clue to a deeper level of reality, one that transcends the limitations of space and time. In recent years, the field of cosmology has also begun to grapple with the possibility that our universe might not be the only one. The concept of the multiverse suggests that our universe is just one of an infinite number of universes, each with its own physical laws and constants. In some versions of this theory, new universes are constantly being created in a process called eternal inflation. In others, the multiverse arises from the many worlds interpretation of quantum mechanics, where every possible outcome of a quantum event leads to the creation of a new universe. While the multiverse remains a highly speculative idea, it offers a potential solution to some of the mysteries of the cosmos, such as the fine-tuning problem. If there are an infinite number of universes, it is not surprising that one of them would have the right conditions for life to exist. Yet, the multiverse theory also raises new philosophical questions. If there are infinite versions of reality, what does that mean for our sense of self and the uniqueness of our universe? Could there be other versions of you living in parallel universes, each experiencing different outcomes based on different choices or events? And if the multiverse is real, how could we ever observe or interact with these other universes? While the idea of a multiverse is tantalizing, it remains far beyond the reach of current scientific observation, leaving it in the realm of theory for now. Another frontier in our exploration of the cosmos lies in the study of gravitational waves. These ripples in spacetime, first predicted by Einstein's theory of general relativity, were directly detected for the first time in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are produced by some of the most violent and energetic processes in the universe, such as the collision of black holes or neutron stars. Their detection opened up a new way of observing the universe, allowing scientists to listen to cosmic events that were previously invisible. This new era of gravitational wave astronomy has the potential to reveal even more about the hidden workings of the universe, from the formation of black holes to the very nature of spacetime itself. The discovery of gravitational waves also brings us closer to understanding one of the most enduring mysteries of the cosmos, the true nature of gravity. While we experience gravity as a force that pulls objects toward one another, our understanding of it remains incomplete. Einstein's general theory of relativity describes gravity as the curvature of spacetime caused by the presence of mass and energy. However, this classical description of gravity does not align with the principles of quantum mechanics, leading to a major unresolved problem in physics. A unified theory of quantum gravity, a theory that combines the physics of the very large, relativity, with the physics of the very small, quantum mechanics, remains one of the greatest challenges in science. Some physicists have proposed that black holes could hold the key to unlocking a theory of quantum gravity. The extreme conditions at the event horizon of a black hole, where spacetime is stretched to its limits, could provide insights into how gravity behaves at the quantum level. One of the most intriguing ideas in this area is the concept of the holographic principle, which suggests that all of the information contained within a volume of space can be represented on the boundary of that space, much like a hologram. This idea has profound implications for our understanding of black holes, spacetime, and even the entire universe. If the holographic principle is correct, it could mean that our three-dimensional universe is actually a projection of information encoded on a two-dimensional surface. The mysteries of the cosmos extend beyond the realm of physics to the nature of life itself. While we have a fairly good understanding of how life emerged and evolved on Earth, the question of whether life exists elsewhere in the universe remains one of the greatest unanswered questions in science. The discovery of extremophiles, organisms that thrive in extreme environments, such as deep-sea hydrothermal vents or acidic hot springs, has expanded our understanding of the conditions under which life can survive. This has fueled the search for life on other planets and moons in our solar system, particularly Mars and the icy moons Europa and Enceladus, which may harbor subsurface oceans. But what about intelligent life? The search for extraterrestrial intelligence, SETI, has been ongoing for decades, with scientists scanning the skies for signals from advanced civilizations. So far, these searches have yielded no conclusive evidence of intelligent life beyond Earth. This has led to a renewed interest in the Fermi paradox, which asks, if intelligent civilizations are common in the universe, why haven't we found any evidence of them? One possible answer is that intelligent life is extremely rare or short-lived. Civilizations may destroy themselves before they have the chance to explore the galaxy, or they may simply not be interested in communicating with us. Other explanations for the Fermi paradox are more speculative. Some suggest that advanced civilizations may be so different from us that we would not recognize their signals even if we detected them. Others propose that there could be a great filter, a stage in the development of life that is extremely difficult to overcome, whether it be the emergence of intelligent life, the development of technology, or the ability to avoid self-destruction. If the great filter lies in our future, it could mean that our civilization is at risk of extinction. If it lies in our past, it could explain why we have not encountered other intelligent civilizations. The mysteries of the cosmos are not limited to questions about life and the universe's structure. They also touch on the deepest philosophical questions about existence itself. One such question is, why is there something rather than nothing? The existence of the universe, with all its complexity and beauty, is something that cannot be easily explained. Some physicists propose that the laws of quantum mechanics allow for the spontaneous creation of universes from nothing, while others suggest that the universe may be eternal, with no beginning or end. Yet, these explanations do not fully satisfy the deeper philosophical question of why there is a universe at all. Another profound mystery is the concept of the anthropic principle, which posits that the universe appears to be fine-tuned for the existence of life because we are here to observe it. In other words, if the universe were not conducive to life, we would not be around to ask these questions. While this may seem like a tautology, it raises deeper questions about the nature of reality and the role of consciousness in the cosmos. Is the universe fine-tuned by chance, or is there a deeper reason for the existence of conscious beings like us? Some scientists and philosophers argue that the anthropic principle hints at the possibility of purpose or design in the universe, while others believe it is simply a reflection of the statistical improbability of our existence in an otherwise indifferent cosmos. As we continue to explore the cosmos, new mysteries are sure to emerge. The advent of new technologies, such as space telescopes and particle accelerators, will allow us to probe deeper into the universe and uncover new clues about its origins, structure, and future. However, it is also possible that some mysteries of the cosmos will remain forever beyond our reach. The universe is vast, complex, and full of surprises, and our understanding of it is still in its infancy. For every question we answer, new questions arise, reminding us that the cosmos is not just a collection of stars and galaxies, but a profound and inexhaustible source of wonder. The mysteries of the cosmos inspire a sense of humility and curiosity. One of the greatest challenges we face in unraveling these mysteries is the limitation of our observational tools. Despite all the advancements in technology, we are still only able to observe a fraction of the universe. The vast majority of the cosmos, nearly 95%, is made up of dark matter and dark energy, entities that we cannot directly observe or measure. This means that the universe as we understand it is primarily composed of phenomena we know almost nothing about, which adds layers of complexity to our quest for understanding. Dark matter is thought to make up about 27% of the universe's total mass and energy. It does not emit, absorb, or reflect light, making it invisible to current detection methods. However, its presence is inferred through its gravitational effects on visible matter. For instance, galaxies rotate at speeds that cannot be accounted for by the amount of visible matter they contain. Dark matter provides the extra gravitational pull needed to explain this discrepancy. Despite decades of research, scientists have yet to identify what dark matter is composed of. Some theories suggest that it consists of weakly interacting massive particles, WIMPs, while others propose more exotic candidates, such as axions or sterile neutrinos. The discovery of dark matter would not only revolutionize our understanding of the cosmos, but also provide insight into the fundamental forces that govern the universe. Even more mysterious than dark matter is dark energy, which accounts for roughly 68% of the universe's total energy content. Dark energy is the name given to the force that is driving the accelerated expansion of the universe. In the 1990s, astronomers discovered that distant galaxies were moving away from us at an ever-increasing rate, a finding that contradicted the expectation that gravity would slow down the expansion of the universe over time. This acceleration suggests that dark energy is pushing the fabric of space apart, but its nature remains a profound enigma. Some theories propose that dark energy is a property of space itself, while others suggest that it could be linked to a new field or particle that we have yet to discover. The precise nature of dark energy is one of the biggest open questions in cosmology, and it has profound implications for the fate of the universe. One possible scenario for the future of the universe, driven by dark energy, is known as the Big Freeze. In this model, the universe continues to expand at an accelerating rate, causing galaxies to move farther and farther apart. As the universe expands, it becomes increasingly cold and empty. Stars burn out, galaxies drift away from one another, and eventually, the universe becomes a dark, frozen wasteland. Over incredibly long timescales, even black holes evaporate due to a process known as Hawking radiation, leaving behind only a cold, diffuse sea of elementary particles. The Big Freeze is a bleak vision of the future, one in which the universe gradually fades into darkness and entropy reaches its maximum possible state. Another possible outcome is the Big Rip. In this scenario, dark energy becomes increasingly dominant over time, causing the expansion of the universe to accelerate so rapidly that even the fundamental forces holding matter together are overcome. Galaxies, stars, planets, and eventually atoms themselves are torn apart by the relentless expansion of space. The Big Rip envisions a universe that is not only cold and empty but also violently destroyed by the very force that drives its expansion. While the Big Rip remains a speculative hypothesis, it serves as a reminder of how little we truly understand about the ultimate fate of the universe. In contrast to these end-of-the-universe scenarios, some cosmologists propose a cyclical model, in which the universe undergoes infinite cycles of expansion and contraction. In this Big Bounce model, the universe expands to a certain point, then contracts under the force of gravity, leading to a new Big Bang and the creation of a new universe. This process could repeat endlessly, with each cycle representing a new universe with its own set of physical laws and constants. While this idea is appealing from a philosophical standpoint, it is still highly speculative and lacks direct observational evidence. The questions surrounding dark matter, dark energy, and the ultimate fate of the universe are just a few of the many cosmic mysteries that challenge our understanding. Another such mystery lies in the very beginning of the universe, the moment of the Big Bang. While the Big Bang theory provides a comprehensive explanation for the evolution of the universe from a hot, dense state to its current form, it leaves unanswered questions about the true nature of the beginning. What caused the Big Bang? Was there a moment before time itself, or is the concept of before meaningless in this context? These questions push the boundaries of both physics and philosophy, as they probe the limits of human understanding. One of the most promising avenues for exploring the early universe is the study of cosmic inflation. This theory suggests that in the first fractions of a second after the Big Bang, the universe underwent a rapid and exponential expansion, smoothing out any irregularities and leading to the large-scale structure we observe today. Inflation provides an elegant solution to some of the puzzles of the Big Bang theory, such as the horizon problem, why distant regions of the universe appear to have the same temperature despite not having had time to exchange information, and the flatness problem, why the universe appears to be geometrically flat on large scales. However, the precise mechanism behind inflation remains unknown, and there is still much debate among physicists about how to test the theory. One of the most intriguing aspects of cosmic inflation is that it could lead to the creation of multiple universes. According to some versions of inflation theory, different regions of space could inflate at different rates, leading to the formation of pocket universes with different physical properties. This idea is closely related to the concept of the multiverse, in which our universe is just one of many, each with its own set of laws and constants. If true, the multiverse would radically alter our understanding of the cosmos, challenging our notions of uniqueness and the anthropic principle. However, like many other cosmological ideas, the multiverse remains speculative, as there is currently no way to directly observe or test its existence. As we push the boundaries of our knowledge, new technologies and observatories are offering unprecedented glimpses into the far reaches of the universe. The James Webb Space Telescope, JWST for example, is designed to observe the universe in the infrared spectrum, allowing scientists to peer through clouds of dust and gas that obscure our view in visible light. The JWST promises to reveal new insights into the formation of stars, galaxies, and planetary systems, as well as provide clues about the atmospheres of exoplanets that could harbor life. With each new discovery, we are reminded that the cosmos is far more complex and mysterious than we could ever have imagined. Exoplanet research has become one of the most exciting fields in astronomy, as scientists search for planets beyond our solar system that could potentially support life. The discovery of thousands of exoplanets in recent years, many of them orbiting in the habitable zone of their stars, where liquid water could exist, has fueled speculation about the existence of extraterrestrial life. Some of the most promising targets for further study include planets in the TRAPPIST-1 system and Proxima Centauri b, a planet orbiting the closest star to our solar system. The development of new technologies, such as the ability to analyze the atmospheres of distant planets, could one day lead to the discovery of biosignatures, chemical indicators of life, on exoplanets. Yet, the search for life raises profound questions about our place in the cosmos. If we do discover evidence of extraterrestrial life, how would that change our understanding of ourselves and our role in the universe? Would we be able to communicate with these other forms of life, or would they be so different from us that meaningful interaction is impossible? And if we find that life is rare or non-existent beyond Earth, what does that say about the uniqueness and significance of our own existence? These are not just scientific questions but also deeply philosophical ones, touching on themes of identity, purpose, and the meaning of life. The mysteries of the cosmos extend far beyond the search for life and the understanding of physical laws. They challenge us to confront the limitations of our knowledge and the nature of reality itself. As we continue to explore the universe, we are reminded of the vastness of what we do not know, and the possibility that some questions may never have definitive answers. Yet, it is in the pursuit of these mysteries that we find meaning and wonder, pushing the boundaries of human curiosity and imagination. The exploration of the cosmos isn't just an adventure into the unknown, but also a journey into the fundamental nature of reality. One of the most confounding aspects of this journey is the nature of time itself. In our daily experience, time seems linear, moving forward, one second after another, but in the realm of cosmology and theoretical physics, time behaves in ways that defy intuition. General relativity, for instance, tells us that time is relative. It can stretch or contract depending on the strength of gravity, or the speed at which an object is moving. Near the event horizon of a black hole, for example, time would pass much more slowly relative to an observer far away. This concept, known as time dilation, has been confirmed through numerous experiments, such as clocks flown on high-speed jets showing slightly less elapsed time than clocks on the ground. But what about time at the very beginning of the universe, at the moment of the Big Bang? Did time even exist before this event, or is time itself a product of the universe's expansion? Some physicists argue that the notion of before the Big Bang is meaningless because time, as we understand it, began with the Big Bang. This idea suggests that asking what happened before the Big Bang is akin to asking what's north of the North Pole, There simply is no before, because time as a concept did not exist. Others propose that the Big Bang could be just one phase in a much larger, perhaps cyclical, universe, where time extends infinitely backward and forward. Quantum mechanics adds yet another layer of complexity to our understanding of time and the cosmos. The famous quantum entanglement phenomenon suggests that particles can be instantaneously connected across vast distances, in apparent violation of the speed of light, a principle thought to be a fundamental limit in the universe. This has led some physicists to speculate that time and space, as we perceive them, might be emergent phenomena rather than fundamental aspects of reality. In other words, the flow of time that we experience could be a kind of illusion, a consequence of deeper quantum processes that we do not yet fully understand. This line of thought leads us to the holographic principle, one of the more speculative but fascinating ideas in modern theoretical physics. The holographic principle suggests that all the information contained in a three-dimensional volume of space can be encoded on a two-dimensional surface at the boundary of that space, much like a hologram. In this view, the entire universe could be a kind of projection from a lower dimensional reality, with time and space emerging as secondary properties. While this idea remains highly theoretical, some researchers believe that it could help reconcile the seemingly incompatible theories of quantum mechanics and general relativity, providing a pathway to the elusive theory of everything that unifies all the fundamental forces of nature. These abstract concepts are not just esoteric musings, but are actively being explored in the context of black holes. Black holes are among the most enigmatic objects in the universe, where gravity is so strong that not even light can escape. According to classical general relativity, the core of a black hole contains a singularity, a point where density becomes infinite, and the known laws of physics break down. However, quantum mechanics suggests that something more complex must be happening. One of the most puzzling paradoxes in modern physics, the black hole information paradox, arises from the apparent conflict between quantum mechanics and general relativity. Quantum theory holds that information about a physical system can never be completely destroyed, yet when matter falls into a black hole, it seems that all the information about that matter is lost forever when the black hole evaporates via Hawking radiation. Resolving this paradox could provide crucial insights into the nature of quantum gravity and the ultimate structure of the universe. The enigma of black holes has only deepened with recent discoveries, such as the detection of gravitational waves, ripples in the fabric of spacetime caused by the collision of massive objects like black holes and neutron stars. The first detection of gravitational waves in 2015 by the LIGO Observatory confirmed a major prediction of Einstein's theory of general relativity and opened a new window into the universe. Through gravitational waves, we can now listen to cosmic events that were previously inaccessible to us, such as the merging of black holes billions of light years away. These observations provide valuable data on the nature of black holes and the behavior of space-time under extreme conditions. One of the most exciting recent developments in the study of black holes was the first-ever image of a black hole, captured by the Event Horizon Telescope, EHT, in 2019. This image showed the shadow of a supermassive black hole at the center of the galaxy M87, surrounded by a glowing ring of gas and dust being pulled toward the event horizon. The ability to directly observe the immediate environment of a black hole is a monumental achievement in astronomy and provides crucial data for testing our theories of gravity and space-time. While black holes may represent the ultimate extreme in gravitational phenomena, they are not the only cosmic objects that challenge our understanding of the universe. Neutron stars, the remnants of massive stars that have undergone supernova explosions, are another class of objects that push the limits of physics. Composed almost entirely of neutrons packed together at incredibly high densities, neutron stars are so compact that a single teaspoon of their material would weigh billions of tons. Neutron stars also exhibit extreme magnetic fields and rapid rotation, with some spinning hundreds of times per second, emitting beams of radiation that we observe as pulsars. The study of neutron stars and pulsars offers valuable insights into the behavior of matter under extreme conditions, where the conventional models of particle physics break down. One of the most mysterious aspects of neutron stars is the possibility of quark stars, or strange stars, objects even more exotic than neutron stars, where the neutrons themselves break down into their constituent quarks. These hypothetical objects, if they exist, would provide a unique window into the fundamental nature of matter and the strong nuclear force that holds atomic nuclei together. The mysteries of the cosmos are not confined to the large-scale structure of the universe or the behavior of extreme objects like black holes and neutron stars. At the opposite end of the scale, we are confronted with profound questions about the nature of the smallest building blocks of reality. The Standard Model of Particle Physics, which describes the behavior of fundamental particles such as quarks, electrons, and photons, has been incredibly successful in explaining a wide range of phenomena. Yet, it is also incomplete, as it does not account for gravity or explain the existence of dark matter. Moreover, the discovery of the Higgs boson in 2012, while confirming a key aspect of the Standard Model, has raised new questions about the stability of the universe. According to some calculations, the mass of the Higgs boson suggests that the universe exists in a metastable state, meaning that it could eventually transition to a more stable state through a process known as vacuum decay. In this scenario, a tiny bubble of true vacuum could form spontaneously in the universe and expand at the speed of light, annihilating everything in its path. While this sounds like the plot of a science fiction movie, it is a real possibility in the framework of quantum field theory. However, it is unlikely to happen anytime soon, as the timescales involved are far longer than the current age of the universe. Nevertheless, the concept of vacuum decay highlights the delicate balance of forces that govern the universe and the potential for sudden, dramatic changes in the fabric of reality. Another area where our understanding of the cosmos remains incomplete is the nature of the fundamental forces that govern the universe. The four known forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are responsible for everything from the behavior of galaxies to the interactions between subatomic particles. Yet, despite their apparent differences, physicists have long sought to unify these forces into a single, overarching theory. The quest for a grand unified theory, GUT, that merges the strong, weak, and electromagnetic forces is one of the central goals of modern physics, but it has proven elusive. Even more challenging is the unification of gravity with the other three forces, a task that would require a theory of quantum gravity. One of the most promising candidates for a theory of quantum gravity is string theory. According to string theory, the fundamental particles of nature are not point-like objects but rather tiny, vibrating strings. These strings can oscillate at different frequencies, with each mode of vibration corresponding to a different particle. In this framework, gravity emerges naturally as one of the possible vibrational modes of the strings. String theory also predicts the existence of additional dimensions beyond the familiar 3 dimensions of space and 1 of time, possibly as many as 10 or 11 dimensions. These extra dimensions are thought to be compactified, meaning they are curled up so small that they are undetectable at human scales. Despite its mathematical elegance and potential to unify the forces of nature, string theory remains highly speculative, and experimental evidence for its predictions has yet to be found. The energy scales required to test many of the predictions of string theory are far beyond the reach of current particle accelerators. Nevertheless, string theory has inspired a vast body of research and has led to new insights into black holes, quantum field theory, and the nature of spacetime itself. One of the more intriguing aspects of string theory is its connection to the multiverse hypothesis. String theory predicts a vast number of possible vacuum states, perhaps as many as 10 to the power of 500, each corresponding to a different set of physical laws and constants. This has led some physicists to propose that our universe is just one of many in a multiverse, with each universe having its own unique properties. In some of these universes, the constants of nature might be different, leading to completely different forms of matter, chemistry, and life. While the multiverse hypothesis is controversial and difficult to test, it offers a possible explanation for why the constants of nature in our universe seem to be fine-tuned for the existence of life. The idea of a multiverse also ties into the concept of cosmic inflation, a theory that seeks to explain the uniformity and large-scale structure of the universe. According to the inflationary model, the universe underwent a brief period of extremely rapid expansion in the first fractions of a second after the Big Bang. This rapid expansion smoothed out any irregularities in the early universe, leading to the homogeneous and isotropic universe we observe today. However, some versions of inflationary theory suggest that inflation never completely stopped but continues in some regions of space, giving rise to pocket universes within a larger multiverse. Inflationary theory has been supported by observations of the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB provides a snapshot of the universe as it was about 380,000 years after the Big Bang when the first atoms were forming, and light could finally travel freely through space. The tiny fluctuations in temperature and density observed in the CMB have provided crucial evidence for inflation and have helped cosmologists refine their models of the early universe. However, there are still many open questions, such as the nature of the inflaton field that is thought to drive inflation and the conditions that caused inflation to end in our region of space. Beyond inflation and the multiverse, other speculative ideas have been proposed to explain the origin and structure of the universe. One such idea is the ekpyrotic model, which suggests that the Big Bang was not the beginning of time but rather the result of a collision between two higher-dimensional branes in a larger, multidimensional space. In this view, the universe undergoes a series of cyclic phases of expansion and contraction, with each cycle beginning with a Big Bang-like event. While this model offers an alternative to inflation, it remains highly theoretical and has yet to be confirmed by observations. Another intriguing concept is the possibility that our universe is a simulation, a notion popularized by philosophers, scientists, and technologists alike. According to the simulation hypothesis, advanced civilizations in the distant future could have the technology to simulate entire universes, including the conscious beings within them. If such simulations are possible, it is argued, there could be many more simulated universes than real ones, making it statistically likely that we are living in a simulation. While this idea may sound like science fiction, it raises profound questions about the nature of reality and our place in the cosmos. Some researchers have even proposed looking for evidence of glitches in the laws of physics, anomalies that could indicate the underlying code of a simulated universe. The notion that we might be living in a simulation also touches on philosophical questions about the nature of consciousness and the mind. Consciousness remains one of the greatest unsolved mysteries in both philosophy and science. Despite advances in neuroscience and cognitive science, we still do not fully understand how subjective experience arises from the physical processes of the brain. Some physicists and philosophers have speculated that consciousness might be a fundamental aspect of the universe, akin to space, time, and matter. This idea, known as panpsychism, suggests that consciousness could be a property of all matter, not just complex biological systems. If true, this would imply that the universe itself might be imbued with some form of consciousness, though perhaps on a scale and level of complexity far beyond our comprehension. The relationship between consciousness and the cosmos has also been explored in the context of the anthropic principle, which suggests that the universe must be compatible with the existence of conscious observers. There are two main versions of the anthropic principle: the weak anthropic principle, which simply states that the universe's laws and constants must be such that conscious life can arise, and the strong anthropic principle, which goes further by suggesting that the universe was in some sense designed, or fine-tuned, for the existence of life. While the anthropic principle is often invoked to explain the apparent fine-tuning of the universe's physical constants, it has been criticized for being unfalsifiable and for potentially halting further scientific inquiry by appealing to the inevitability of life in a universe capable of supporting it. The fine-tuning of the universe is one of the most profound and perplexing mysteries in cosmology. For example, if the force of gravity were just a tiny bit stronger or weaker, stars might never have formed, or the universe might have collapsed back in on itself. Similarly, if the electromagnetic force were slightly different, atoms and molecules, essential for chemistry and life, might not exist. These and other examples of fine-tuning have led some scientists and philosophers to suggest that the universe appears to be set up in a way that allows for the existence of life. However, whether this fine-tuning is the result of a multiverse, some deeper physical principle, or something more mysterious remains an open question. As we venture further into the unknown, we must also confront the possibility that some of the mysteries of the cosmos may never be fully understood. The limitations of human cognition, the finite speed of light, and the vastness of the universe mean that there are likely regions of the cosmos that are forever beyond our reach. For instance, due to the accelerated expansion of the universe driven by dark energy, distant galaxies are receding from us faster than the speed of light, making them inaccessible to observation. In the distant future, the universe may become so stretched out that all other galaxies will disappear from view, leaving only a dark, empty void. This accelerated expansion also raises profound questions about the ultimate fate of the universe. Several possible scenarios have been proposed, including the Big Freeze, where the universe continues to expand and cool until all matter is spread so thin that no new stars or galaxies can form, leading to a cold, dark, and lifeless cosmos. Another possibility is the Big Rip, where the expansion of the universe accelerates to the point that it tears apart galaxies, stars, planets, and even atoms. Alternatively, the universe could eventually stop expanding and begin to contract, leading to a Big Crunch, where all matter and energy collapse back into a singularity, possibly giving rise to a new Big Bang and a new universe. Despite these grim possibilities, there is also a sense of wonder and awe that comes with contemplating the vastness and complexity of the cosmos. Each new discovery, whether it be the detection of gravitational waves, the imaging of a black hole, or the observation of distant exoplanets, adds another piece to the puzzle of our understanding. Yet, for every answer we find, new questions arise, ensuring that the mysteries of the cosmos will continue to captivate and challenge us for generations to come. As we look to the future, the next great leaps in our exploration of the cosmos may come from advancements in technology and space travel. Missions to other planets, such as Mars, are already on the horizon, and the search for life beyond Earth remains one of the most compelling endeavors in modern science. Whether life exists elsewhere in the universe, on Mars, on the icy moons of Jupiter and Saturn, or on distant exoplanets orbiting other stars, remains one of the greatest unanswered questions of all time. The discovery of extraterrestrial life, even in its most basic microbial form, would have profound implications for our understanding of biology, evolution, and the uniqueness of life on Earth. The search for life beyond Earth is closely tied to the search for habitable exoplanets, planets that orbit stars outside our solar system and have conditions suitable for life as we know it. In recent years, astronomers have discovered thousands of exoplanets, some of which fly in the habitable zone of their parent star, where temperatures are just right for liquid water to exist. Future telescopes, such as the James Webb Space Telescope and the Extremely Large Telescope, will allow us to study the atmospheres of these exoplanets in unprecedented detail, searching for signs of life, such as the presence of oxygen, methane, or other biosignatures. The discovery of life on an exoplanet would be nothing short of revolutionary, altering our understanding of biology, the uniqueness of Earth, and the potential for life to exist in a variety of environments. However, even if we don't find life as we know it, the diversity of planets and moons already discovered suggests that the cosmos may hold an astonishing array of environments. Some scientists have even proposed that life could exist in forms we cannot yet conceive. Perhaps life based on chemical systems other than carbon, or even forms of life that are not biological in the traditional sense. The study of exoplanets is also providing new insights into the history of our own solar system. By observing planets in other star systems, astronomers can compare them to the planets orbiting our Sun, leading to a better understanding of how planetary systems form and evolve. Some of the exoplanets discovered so far are vastly different from anything in our solar system, so-called hot Jupiters, that orbit extremely close to their stars, or super-Earths. that are more massive than Earth but smaller than Neptune. These exotic worlds challenge existing models of planet formation and hint at the incredible diversity of planetary systems that may exist in the galaxy. One of the biggest unsolved mysteries in this field is the question of how common Earth-like planets are. Although we have discovered many exoplanets, the exact prevalence of rocky planets in the habitable zone of their stars remains an open question. The Kepler Space Telescope, which was designed to find such planets, has greatly expanded our knowledge in this area, but the data we have so far suggests that Earth-like planets might be relatively rare. This raises profound questions about the likelihood of finding life elsewhere in the universe and whether the conditions that allowed life to arise on Earth are unique or ubiquitous. At the same time, the possibility exists that life could thrive in environments very different from Earth's. Some researchers are exploring the idea of shadow biospheres, hypothetical forms of life that might exist on Earth or elsewhere in the solar system but have remained undetected because they are based on alternative biochemistries. For example, life might exist on the icy moons of Jupiter and Saturn, such as Europa or Enceladus, where subsurface oceans could provide the conditions for microbial life. Missions like the Europa Clipper and future explorations of Enceladus aim to probe these moons for signs of life, possibly by sampling the plumes of water vapor that erupt from their icy surfaces. Closer to home, the study of astrobiology, life in the universe, includes examining the possibility that life once existed on Mars. The red planet has long fascinated scientists because of the evidence that liquid water once flowed on its surface. Although the planet is now cold and dry, with a thin atmosphere, there are signs that underground water reservoirs might still exist, and ancient Mars may have had a much more Earth-like climate. The discovery of ancient microbial life on Mars would provide tantalizing clues about the potential for life to exist elsewhere in the cosmos, and could offer insights into the conditions necessary for life to begin. As we look for life beyond Earth, we are also beginning to question our assumptions about what forms life might take. One of the great questions in biology is whether life is a universal phenomenon, whether it will arise wherever the conditions are right, or whether life on Earth is the result of an extraordinarily rare combination of factors. Some scientists argue that life might be relatively easy to form, as long as liquid water and the right chemical ingredients are present. Others believe that the emergence of life might require a highly specific set of circumstances, making it an exceedingly rare event. The discovery of life, or even the lack of it, would have profound implications for humanity. If we find life beyond Earth, it would confirm that the universe is teeming with biological diversity. If we failed to find life, it would raise the question of why Earth is so special and could suggest that we are indeed alone in the cosmos. Either way, the search for life is one of the great scientific endeavors of our time, one that challenges our assumptions about biology, chemistry, and the nature of life itself. In addition to the search for life, another key area of exploration in the mysteries of the cosmos is the nature of black holes. Black holes represent the ultimate mystery in astrophysics, regions of space where gravity is so strong that not even light can escape. They are formed when massive stars exhaust their nuclear fuel and collapse under the force of their own gravity. This collapse compresses the matter in the star to a point of infinite density, known as a singularity, surrounded by an event horizon, the point beyond which nothing can escape. The existence of black holes was first predicted by Einstein's theory of general relativity, and their presence has since been confirmed by multiple lines of evidence, including the observation of stars orbiting unseen objects and the detection of gravitational waves produced by black hole mergers. However, the nature of the singularity at the center of a black hole remains one of the great unsolved problems in physics. General relativity predicts that the density of matter becomes infinite at the singularity, a result that suggests the theory breaks down in this extreme environment. Physicists are still searching for a theory of quantum gravity that could reconcile the laws of quantum mechanics with general relativity and provide a clearer understanding of what happens inside a black hole. One of the most remarkable recent discoveries related to black holes is the detection of gravitational waves. In 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, made the first ever observation of these ripples in spacetime, produced by the collision of two black holes. This discovery confirmed a key prediction of Einstein's theory of general relativity and opened up an entirely new way of observing the universe. Gravitational waves provide a unique window into some of the most violent and energetic events in the cosmos, including the mergers of black holes and neutron stars, and they offer the potential to probe the universe in ways that were previously impossible. The study of black holes has also led to some of the most bizarre and mind-bending ideas in modern physics. One such idea is the concept of the information paradox. According to the laws of quantum mechanics, information cannot be destroyed. However, when an object falls into a black hole, it appears that all the information about its structure is lost to the outside universe. This presents a fundamental conflict between general relativity and quantum mechanics, leading to intense debates about the fate of information inside black holes. Some physicists have proposed that information might be preserved on the event horizon of the black hole, encoded in a two-dimensional form, an idea known as the holographic principle. This concept suggests that the entire three-dimensional volume of the black hole might be described by information stored on its two-dimensional surface, a radical proposal that has far-reaching implications for our understanding of space, time, and reality itself. Black holes are also thought to play a key role in the evolution of galaxies. Observations suggest that most, if not all, large galaxies harbor supermassive black holes at their centers. These black holes, which can have masses millions or even billions of times that of the Sun, are thought to influence the formation and growth of galaxies through their immense gravitational pull and the energetic jets of material they produce. Understanding the relationship between black holes and galaxies is an active area of research, and future observations of supermassive black holes, such as the one at the center of our own Milky Way galaxy, could provide important clues about the evolution of the cosmos. Another enigmatic aspect of the universe that remains poorly understood is the nature of dark matter and dark energy. Together, these two components are thought to make up about 95% of the total energy content of the universe, yet their true nature remains elusive. Dark matter is thought to be a form of matter that does not emit or absorb light, making it invisible to telescopes. However, its presence can be inferred from its gravitational effects on visible matter, such as the rotation of galaxies and the bending of light from distant objects. Despite extensive efforts to detect dark matter particles directly, they have so far remained elusive. The leading candidates for dark matter include weakly interacting massive particles, WIMPs, and axions, but no definitive evidence has been found for either. The search for dark matter continues, with experiments designed to detect the rare interactions between dark matter particles and ordinary matter, as well as efforts to understand the role of dark matter in the formation of galaxies and large-scale cosmic structures. Dark energy, on the other hand, is even more mysterious. It is thought to be responsible for the accelerated expansion of the universe, but its exact nature is unknown. Some theories suggest that dark energy could be a property of space itself, a cosmological constant, introduced by Einstein to account for the observed acceleration. Others propose that dark energy might be the result of a new, undiscovered force or field that permeates the universe. Understanding dark energy is one of the greatest challenges in modern cosmology, as it holds the key to the ultimate fate of the universe. The discovery of dark energy and dark matter has profoundly changed our understanding of the cosmos, forcing us to confront the possibility that the vast majority of the universe is made up of unknown and invisible substances. These discoveries challenge our understanding of fundamental physics and raise profound questions about the nature of reality and the limits of human knowledge. The role of dark matter and dark energy in the universe's evolution has opened up a new frontier in astrophysics and cosmology. While dark matter helps to hold galaxies together with its gravitational influence, dark energy appears to be driving the expansion of the universe at an accelerating pace. This expansion is a relatively recent discovery, with astronomers observing that distant galaxies are moving away from us faster than nearby ones. The deeper we look into space, the faster everything seems to be receding, suggesting that something is counteracting the gravitational pull that should be slowing down the universe's expansion. The exact nature of dark energy is one of the greatest unsolved mysteries in science today. We know it makes up approximately 68% of the universe's total energy, yet its behavior remains almost completely unknown. Theoretical physicists have put forward several ideas, but none fully explain its properties. One possibility is that dark energy is a new form of energy inherent to space itself, increasing as the universe expands, creating more and more space as time progresses. This idea suggests that, rather than being a force exerted by some unknown particle, dark energy may be woven into the fabric of space-time itself. Another possibility is that dark energy represents some kind of quintessence field, a dynamic, evolving energy field that pervades all of space. Unlike the cosmological constant, which remains the same throughout the universe's history, quintessence would evolve over time, potentially altering the fate of the cosmos in ways we do not yet fully understand. If dark energy is indeed a dynamic force, it could eventually reverse the universe's expansion or cause it to accelerate even faster, leading to different end scenarios for the cosmos. These questions about the fate of the universe bring us to the ultimate mystery: how will the universe end? The eventual destiny of the cosmos depends on the nature of dark energy, dark matter, and the fundamental forces governing the universe. There are several competing theories about the universe's ultimate fate, ranging from a slow heat death to a more violent conclusion. One of the leading theories is the so-called Big Freeze, or heat death, scenario. In this scenario, the universe continues expanding indefinitely, driven by dark energy. As space expands, galaxies will move farther and farther apart, eventually becoming so distant from one another that no new stars can form. The existing stars will burn out, and the universe will become a cold, dark, and empty place. Over billions and trillions of years, the matter will decay, black holes will evaporate through a process known as Hawking radiation, and all that will remain will be an exceedingly dilute soup of subatomic particles, slowly drifting through an ever-expanding void. Another possibility is the Big Rip. In this scenario, dark energy grows stronger over time, eventually overcoming all the other forces in the universe. Galaxies, stars, and even atoms themselves could be torn apart by the accelerating expansion of space. If dark energy behaves in this way, the universe could end in a cataclysmic event where all matter is shredded apart at an increasingly rapid pace. The timeline for such an event is uncertain, but it could occur in tens of billions of years, if at all. A third possibility is the Big Crunch, though this idea has fallen out of favor in recent years. In this model, the expansion of the universe eventually reverses, and the universe begins to collapse in on itself. This could happen if the effects of dark energy diminish over time, or if gravity eventually wins out over the expansion of space. The universe would contract, heating up as galaxies, stars, and planets are compressed together. In the final moments, the entire universe would collapse into an extremely hot and dense state, possibly leading to another Big Bang and the birth of a new universe. There is also the Big Bounce theory, which suggests that the universe undergoes endless cycles of expansion and contraction. After each big crunch, a new Big Bang occurs, leading to a new period of cosmic expansion. This idea, while speculative, offers a potential way to reconcile the origin of the universe with the laws of physics and the possibility of eternal cycles of cosmic rebirth. It would mean that our universe is just one phase in an infinitely repeating cosmic cycle, where each cycle could give rise to new physical laws, constants, and even forms of matter. In contrast to these dramatic scenarios, some scientists propose that the universe may exist in a steady state, governed by unknown laws that prevent its ultimate demise. This view, often associated with the idea of the multiverse, suggests that our universe is just one of many, and that its apparent expansion and possible end are part of a larger, more complex cosmic system. In this model, the universe might never truly end, as it could be continuously refreshed by processes occurring in parallel universes or higher dimensional spaces. The idea of a multiverse is one of the most fascinating and controversial theories in modern cosmology. According to this hypothesis, our universe is just one of countless other universes that exist in a vast multiverse. Each of these universes could have its own laws of physics, constants, and dimensions, leading to an unimaginable variety of possible realities. The multiverse idea arises naturally from several theories in physics, including string theory and the inflationary model of the early universe. In the inflationary model, the universe underwent a brief period of rapid expansion shortly after the Big Bang. This inflationary phase could have caused pocket universes to form, each with its own unique properties. Some regions of space may have continued to expand indefinitely, while others, like our own universe, slowed down and cooled enough for galaxies, stars, and planets to form. The multiverse concept suggests that what we perceive as the entire universe is just one small part of a much larger and more complex cosmic structure. If the multiverse exists, it raises profound questions about the nature of reality and our place within it. Are there other versions of ourselves in parallel universes? Do different universes have different physical constants, leading to entirely different forms of matter and life? Could some universes be governed by entirely different laws of physics, where time flows backward, or where gravity is repulsive rather than attractive? The answers to these questions are beyond the reach of current science, but they offer a tantalizing glimpse into the potential vastness and complexity of the cosmos. The multiverse theory also intersects with the idea of the anthropic principle, which seeks to explain why the universe appears to be finely tuned for the existence of life. Some physicists argue that the physical constants of our universe, such as the strength of gravity and the charge of the electron, are precisely what they need to be for life to arise. If any of these constants were slightly different, stars might not form, or atoms might not hold together, and life as we know it would be impossible. The anthropic principle suggests that the reason we observe a universe finely tuned for life is that, out of the many possible universes in the multiverse, we happen to live in one where the conditions are right for life to evolve. In this view, our universe is not unique or special. It is simply one of the few that happen to have the right properties for observers like us to exist. This idea has sparked intense debate, as it challenges the traditional view that the universe is governed by a single set of universal laws and raises questions about the limits of scientific explanation. As we explore the mysteries of the cosmos, we also encounter profound questions about the nature of time and space. Time, as we experience it, seems to flow in one direction, from the past to the future. However, the laws of physics do not seem to impose a strict arrow of time. In fact, many physical processes are time-symmetric, meaning they work the same way whether time moves forward or backward. This has led some physicists to question whether the flow of time is a fundamental feature of the universe, or whether it is an emergent property that arises from the way we perceive the universe. The nature of time becomes even more mysterious when we consider the possibility of time travel. While time travel remains a staple of science fiction, some theoretical physicists have explored whether it is possible within the framework of general relativity and quantum mechanics. Wormholes, hypothetical tunnels through spacetime, could, in theory, allow for shortcuts between different points in space and time, creating the possibility of time travel. However, the practical challenges of creating or navigating such a wormhole are immense, and most scientists remain skeptical that time travel could ever be achieved. Even more enigmatic is the concept of the block universe, a model of reality in which time is treated as a dimension similar to space. In this view, the past, present, and future all exist simultaneously, with time as just another coordinate in the fabric of spacetime. From the perspective of the block universe, time does not flow at all. Instead, every moment in time is just as real as every point in space. This idea challenges our everyday experience of time and raises questions about the nature of free will, causality, and the structure of reality itself. The concept of a block universe touches on one of the most perplexing philosophical questions in cosmology. Is the future predetermined, or is it open to change? If every moment in time exists simultaneously in a four-dimensional space-time continuum, as the block universe suggests, then the future may already be set. This could imply that free will is an illusion, and our actions are merely part of a preordained sequence of events. However, this deterministic view of time contrasts with our intuitive experience of making choices and influencing the future. The interplay between quantum mechanics and time introduces even more complexity into this discussion. In the quantum world, particles do not follow definite paths from the past to the future. Instead, they exist in a superposition of multiple possibilities until they are observed or measured. This unpredictability suggests that the future may not be predetermined at all but rather a range of potential outcomes that collapse into a single reality when observed. The famous thought experiment known as Schrödinger's cat encapsulates this strange idea. Until we observe it, the cat in the box is both alive and dead at the same time, existing in two states simultaneously. Quantum mechanics, with its uncertainty and probabilistic nature, seems to offer a different view of the cosmos compared to the deterministic universe described by classical physics. This brings us to the mystery of quantum entanglement, another baffling phenomenon that challenges our understanding of time and space. When two particles become entangled, they remain connected in such a way that the state of one particle instantaneously affects the state of the other, regardless of the distance separating them. This spooky action at a distance, as Einstein famously called it, suggests that information can be transmitted faster than the speed of light, defying the limits imposed by relativity. Entanglement seems to imply that distant parts of the universe can be instantaneously connected, blurring the boundaries between space and time. This phenomenon has been experimentally confirmed in numerous studies, yet its implications for our understanding of the universe remain mysterious. How can information be exchanged instantaneously between entangled particles? And what does this tell us about the underlying nature of reality? Some physicists believe that entanglement may hold the key to a deeper, more fundamental theory of the universe, one that unites quantum mechanics and general relativity into a unified framework, sometimes referred to as the theory of everything. The search for a theory of everything is one of the most ambitious and elusive quests in modern physics. It aims to reconcile the two pillars of 20th century science, quantum mechanics, which describes the behavior of particles on the smallest scales, and general relativity, which explains the structure of space-time and the force of gravity on the largest scales. These two theories, while both incredibly successful in their respective domains, are fundamentally incompatible with each other. Quantum mechanics operates in a probabilistic, discrete world, while general relativity describes a smooth, continuous space-time fabric. Several approaches have been proposed to bridge this gap, including string theory and loop quantum gravity. String theory posits that all particles in the universe are not point-like objects, as traditionally thought, but rather tiny, vibrating strings. The different vibrational modes of these strings give rise to the various particles and forces observed in nature. String theory also requires the existence of additional spatial dimensions beyond the familiar three dimensions of space and one of time, which may be compactified or hidden from our everyday experience. While string theory offers a promising path toward unifying quantum mechanics and gravity, it remains largely speculative and has yet to make experimentally testable predictions. Nonetheless, it has captured the imagination of many physicists, as it could provide a framework for understanding some of the deepest mysteries of the cosmos, including the nature of black holes, the Big Bang, and even the multiverse. Loop quantum gravity, another contender in the search for a theory of everything, takes a different approach. It attempts to quantize space-time itself, proposing that space is not continuous but made up of tiny, discrete loops or quanta of space. This approach suggests that space-time has a granular structure, with a minimum possible size at the Planck scale, far smaller than anything we can currently observe. Loop quantum gravity has had some success in explaining certain aspects of black hole thermodynamics and the early universe, but it too faces significant challenges in making testable predictions. These theoretical frameworks highlight just how much we still have to learn about the fundamental nature of reality. The mysteries of the cosmos extend far beyond the visible stars and galaxies, reaching into the very fabric of space-time and the quantum world that underlies it. As we push the boundaries of our understanding, we are constantly confronted with new questions and paradoxes, challenging us to rethink our most basic assumptions about the universe. One such paradox is the information paradox associated with black holes. Black holes are regions of space where gravity is so intense that not even light can escape, making them invisible to direct observation. According to general relativity, anything that falls into a black hole is lost forever, its information erased from the universe. However, this idea clashes with a fundamental principle of quantum mechanics known as the unitarity principle, which states that information must be preserved in any physical process. This apparent conflict between general relativity and quantum mechanics has given rise to the black hole information paradox. If information is lost when something falls into a black hole, then the laws of quantum mechanics must break down. But if information is preserved, then our understanding of black holes and gravity may need to be revised. This paradox has led to intense debate among physicists, with some proposing that information is stored on the event horizon of a black hole in the form of holographic data, while others suggest that black holes may eventually evaporate, releasing the information back into the universe. The resolution of the black hole information paradox could have profound implications for our understanding of the cosmos, offering new insights into the nature of space, time, and the fundamental forces that govern the universe. It may also provide clues about the true nature of gravity, which remains one of the least understood forces in physics. Gravity, while familiar to us all, is remarkably weak compared to the other fundamental forces, such as electromagnetism and the strong nuclear force. One mystery that has puzzled physicists is why gravity is so weak relative to these other forces. This discrepancy, known as the hierarchy problem, has led some researchers to propose that gravity may be leaking into extra dimensions beyond the familiar three-dimensional space. In this scenario, the apparent weakness of gravity in our universe could be explained by the fact that it spreads out across these hidden dimensions, diluting its strength in the process. If these extra dimensions exist, they could have profound implications for the structure of the universe and our place within it. Some theories even suggest that entire parallel universes could exist within these extra dimensions, hidden from our view but potentially influencing our own universe in subtle ways. The idea of extra dimensions is a key feature of string theory and other attempts to unify gravity with the other fundamental forces, offering a tantalizing glimpse into the possible hidden structure of the cosmos. As we continue to explore these deep mysteries, we are constantly reminded of how little we truly know about the universe. Each new discovery seems to raise more questions than it answers, revealing new layers of complexity and wonder. The cosmos is a vast, mysterious, and ever-evolving tapestry of forces, particles, and dimensions, filled with puzzles that challenge our understanding and inspire us to keep searching for answers. From the invisible dark matter that holds galaxies together to the enigmatic dark energy driving the universe's expansion, from the strange behavior of quantum particles to the mind-bending possibilities of time travel and parallel universes, the mysteries of the cosmos are as profound as they are awe-inspiring. Our quest to understand these mysteries is far from over, and as we push the boundaries of science and technology, we will undoubtedly encounter new and even more puzzling questions. Ultimately, the mysteries of the cosmos remind us of our place in the universe, not as masters of nature, but as curious observers, striving to unravel the secrets of the stars. In doing so, we gain not only a deeper understanding of the universe itself but also a greater appreciation for the beauty, complexity, and interconnectedness of all things. The cosmos is not just a collection of objects in space. It is a living, dynamic entity, filled with surprises and governed by laws that we are only beginning to grasp. As our knowledge grows, so too does our sense of wonder. The more we learn, the more we realize how much there is still to discover. And in that endless journey of exploration and discovery, we find our place in the grand story of the universe. A story that has been unfolding for billions of years and will continue to unfold for billions more. Our journey through the cosmos continues to lead us deeper into its mysteries, revealing not only the vastness of the universe but also its underlying complexity and subtlety. We've already touched upon some of the most confounding questions in cosmology, including the nature of time, quantum mechanics, and the paradoxes surrounding black holes. But the cosmos holds even more profound mysteries, those that stretch beyond our current scientific understanding and challenge the very foundations of what we consider possible. One such mystery is the origin of the universe itself. The Big Bang Theory, The most widely accepted explanation for the beginning of the universe posits that the cosmos began as an infinitely small, hot, and dense point, which then rapidly expanded. This model has been remarkably successful in explaining many observable phenomena, such as the cosmic microwave background radiation, the afterglow of the Big Bang, and the large-scale structure of the universe. However, the Big Bang theory leaves many questions unanswered. Chief among them is the nature of the singularity from which the universe emerged. The concept of a singularity, where the laws of physics break down, suggests that at the very beginning of the universe, space and time as we know them did not exist. This raises the profound question, what, if anything, existed before the Big Bang? Was there a before at all, or did time itself begin with the Big Bang? Some cosmologists speculate that the Big Bang might not have been a unique event. Instead, it could have been part of a larger, cyclical process, where the universe undergoes periods of expansion and contraction, collapsing into a singularity, and then exploding into a new phase of expansion. This idea is known as the cyclic model, or the Big Bounce. If true, the Big Bounce suggests that the universe has no beginning or end in the traditional sense. Instead, it undergoes an eternal series of rebirths, with each cycle producing a new universe with different physical properties. However, evidence for this model is still speculative, and the idea of a pre-Big Bang universe remains one of the most tantalizing and elusive questions in cosmology. In addition to the question of the universe's origins, there is the enigma of its ultimate fate. Just as the universe had a beginning, it may also have an end. But what form will that end take? There are several competing theories about the ultimate fate of the universe, each depending on the amount of matter and energy it contains. One possible scenario is the Big Crunch, where the gravitational attraction of all the matter in the universe eventually causes it to stop expanding and begin contracting. In this scenario, galaxies, stars, and planets would be pulled back together, and the universe would collapse into a singularity, possibly leading to another Big Bang. This cyclical view of the universe is appealing to those who believe that time and space are eternal, but current observations suggest that the universe's expansion is accelerating, making the Big Crunch less likely. A more widely accepted theory is the Big Freeze, or heat death, scenario. In this model, the universe will continue to expand indefinitely, but as it does so, galaxies will move farther apart, stars will burn out, and matter will become increasingly diffuse. Eventually, the universe will reach a state of maximum entropy, where all energy is evenly distributed, and no further work or life-sustaining processes can occur. The universe would become a cold, dark, and lifeless void, with only the faint remnants of once brilliant stars and galaxies scattered across an empty expanse. An even more dramatic end is the Big Rip hypothesis. According to this theory, if the rate of expansion continues to accelerate due to the influence of dark energy, the fabric of spacetime itself could eventually be torn apart. In the distant future, galaxies, stars, planets, and even atoms could be ripped apart by the relentless expansion of the universe. This would represent the ultimate disintegration of everything in the cosmos, leaving behind nothing but isolated particles. Each of these possible fates highlights the profound uncertainty surrounding the future of the universe. While we have made great strides in understanding the cosmos, the forces driving its evolution, such as dark energy, remain mysterious. Dark energy, which appears to be responsible for the accelerated expansion of the universe, makes up roughly 70% of the total energy content of the cosmos, yet we know almost nothing about its nature. It does not interact with matter in the same way that other forces do, and it cannot be directly observed. Instead, its existence is inferred from the effects it has on the expansion of the universe. The discovery of dark energy in the late 20th century was one of the most shocking and transformative events in cosmology. Prior to its discovery, scientists believed that the universe's expansion was slowing down due to the gravitational pull of matter. However, observations of distant supernovae revealed that the expansion was actually speeding up, suggesting the presence of a previously unknown force. This force, dubbed dark energy, is now thought to be the dominant influence on the large-scale structure of the universe, yet its origins and properties remain one of the greatest unsolved mysteries in physics. In addition to dark energy, there is the equally perplexing mystery of dark matter. Unlike dark energy, which drives the expansion of the universe, dark matter is thought to exert a gravitational pull that holds galaxies and galaxy clusters together. Without dark matter, galaxies would not have enough visible mass to prevent them from flying apart due to their rotational speeds. However, dark matter does not emit, absorb, or reflect light, making it invisible to telescopes. Its presence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Dark matter is estimated to make up about 27% of the universe's total mass and energy content, yet we still do not know what it is made of. Various candidates have been proposed, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos, but so far, none have been definitively detected. The search for dark matter continues, with experiments around the world attempting to detect these elusive particles through direct or indirect methods. The discovery of dark matter would represent a major breakthrough in our understanding of the universe, potentially shedding light on the formation of galaxies, the behavior of gravitational forces, and the overall structure of the cosmos. The mysteries of dark matter and dark energy highlight the fact that the vast majority of the universe is made up of substances we cannot directly observe. In fact, only about 5% of the universe is composed of ordinary matter, the familiar atoms and molecules that make up stars, planets, and living organisms. The rest of the cosmos is hidden from view, governed by forces and particles that we have yet to fully comprehend. These unseen forces raise profound questions about the nature of reality itself. Is the universe we observe only a small part of a much larger, hidden reality? Could there be other dimensions or parallel universes that exist beyond our perception? Theories such as string theory suggest that extra dimensions may exist, but they are so small and compactified that we cannot directly observe them. These hidden dimensions could hold the key to unifying the forces of nature, explaining the behavior of dark matter and dark energy, or even revealing the existence of parallel universes, entirely separate realms with different physical laws and constants. The idea of parallel universes, or the multiverse, is one of the most speculative and intriguing concepts in modern cosmology. According to some interpretations of quantum mechanics, every time a quantum event occurs, the universe splits into multiple branches, each representing a different possible outcome. This leads to the idea that there may be an infinite number of parallel universes, each with its own version of reality. In some universes, the laws of physics may be slightly different, leading to alternate histories and outcomes. In others, the differences may be so profound that life, as we know it, could not exist. The concept of the multiverse raises deep philosophical and scientific questions about the nature of existence. If parallel universes exist, could they ever interact with our own? Are there alternate versions of ourselves living out different lives in these other realms? And if there are infinite universes, what does that say about the uniqueness of our own universe and the possibility of life elsewhere in the cosmos? The idea of the multiverse is not just a theoretical curiosity. It has practical implications for our understanding of the universe's fine-tuning. Many aspects of the universe's physical laws and constants seem to be perfectly calibrated to allow for the existence of life. If the strength of gravity were slightly different, or if the charge of the electron were just a little bit off, stars might not form, and planets capable of supporting life would not exist. This fine-tuning has led some to suggest that the universe was designed with life in mind, while others propose that we simply live in one of many universes, most of which are inhospitable to life. In this view, we just happen to exist in a universe where the conditions are right, but there may be countless other universes where life never emerged. The notion of the multiverse serves as a tantalizing explanation for the fine-tuning of the cosmos, but it also challenges our most basic assumptions about the nature of reality. If an infinite number of universes exist, does that diminish the specialness of our own? Or does it suggest that our universe is just one of many possible outcomes, each playing out in parallel? This concept invites us to question whether the laws of physics are as fixed and immutable as they appear, or whether they vary across different universes, resulting in entirely distinct forms of existence. One of the most mysterious and compelling implications of the multiverse theory is its connection to the anthropic principle. The anthropic principle, in its simplest form, states that the universe must be compatible with the existence of observers because we are here to observe it. In other words, the reason the universe seems so finely tuned for life is that if it weren't, we wouldn't be around to notice it. In a multiverse scenario, the anthropic principle becomes even more powerful. Out of countless universes, we just happen to inhabit one that supports life because it is one of the few, or possibly the only, universes where conditions allow for our existence. Yet, even if the multiverse explains the fine-tuning of our universe, it raises another profound question: how can we ever know if parallel universes exist? If they are entirely separate from our own, with no possible interaction, then detecting or proving their existence may be impossible. This leads to a philosophical debate about whether science should concern itself with hypotheses that are, by their very nature, untestable. Some physicists argue that the multiverse is a legitimate scientific concept because it arises naturally from established theories like string theory and quantum mechanics. Others contend that it is purely speculative, and without empirical evidence, it falls outside the realm of science. Regardless of the multiverse's scientific status, it serves as a powerful reminder of the sheer scale and complexity of the cosmos. Our universe, vast and ancient as it is, may be just one of countless others, each with its own unique history and destiny. Whether or not we ever find definitive evidence of parallel universes, the concept challenges us to think beyond the boundaries of our observable world and consider the possibility that reality is far more complex and varied than we can currently imagine. As we continue to explore the mysteries of the cosmos, we are constantly reminded of the limits of our knowledge. Every new discovery raises new questions, and every answer seems to lead to more profound mysteries. One of the most intriguing of these mysteries is the nature of time itself. Time is a fundamental aspect of our experience of the universe, yet its true nature remains elusive. We experience time as a linear progression, moving inexorably from the past to the future, but this may be an illusion. According to Einstein's theory of relativity, time is not an absolute, fixed quantity but is relative to the observer's motion and the presence of gravitational fields. This means that time can slow down or speed up depending on the conditions of the surrounding environment. For example, a clock on a satellite orbiting Earth runs slightly faster than a clock on the planet's surface due to the weaker gravitational field in space. This phenomenon, known as time dilation, has been confirmed through numerous experiments and is an essential consideration in the operation of technologies like GPS. But relativity also suggests that time is not a one-way street. In the context of spacetime, the past, present, and future all exist simultaneously, as part of a four-dimensional continuum. From this perspective, the flow of time may be an illusion created by our limited perception. This idea is further supported by certain interpretations of quantum mechanics, where particles can appear to move backward in time or exist in multiple states simultaneously, defying our everyday understanding of causality. The possibility that time is not as straightforward as it seems raises profound questions about the nature of reality and our place in it. Could time travel be possible? If time is a dimension like space, could we, in theory, move through it in the same way we move through space? These questions have fascinated scientists and philosophers for centuries, and while time travel remains firmly in the realm of science fiction, it is not entirely ruled out by the laws of physics. Certain solutions to Einstein's equations of general relativity, such as rotating black holes or wormholes, suggest that time travel could be possible under very specific conditions. Wormholes, in particular, are hypothetical shortcuts through spacetime that could, in theory, allow for travel between distant regions of the universe, or even between different times. However, creating or finding a stable, traversable wormhole would require technology far beyond anything we currently possess, and many physicists believe that such structures would be inherently unstable, collapsing before any information or matter could pass through. Even if time travel were possible, it raises a host of paradoxes and philosophical dilemmas. The classic grandfather paradox asks what would happen if a time traveler went back in time and prevented their grandfather from meeting their grandmother. If the time traveler's grandfather never met their grandmother, the time traveler would never have been born, and thus would not exist to travel back in time in the first place. This kind of causal loop seems to defy logic, and various solutions have been proposed, ranging from the idea that time travelers create alternate timelines to the suggestion that the universe prevents such paradoxes from occurring through some as yet unknown mechanism. These paradoxes hint at the deep and unresolved mystery surrounding time, causality, and the fabric of the universe itself. While time travel may remain speculative for now, the study of time continues to reveal new insights into the workings of the cosmos. One particularly intriguing area of research is the concept of time symmetry in quantum mechanics. In many quantum systems, the fundamental laws of physics appear to be symmetric with respect to time. That is, they do not distinguish between the past and the future. This suggests that, at a fundamental level, time may not flow in one direction but is instead reversible. If time is symmetric, why do we experience it as moving in only one direction, from past to future? The answer may lie in the concept of entropy. According to the second law of thermodynamics, entropy, a measure of disorder, always increases in a closed system. This increase in entropy gives rise to the arrow of time, the direction in which events seem to unfold. The arrow of time points from lower entropy, more ordered states, to higher entropy, more disordered states, creating the impression of a forward-moving progression. However, the relationship between time, entropy, and the arrow of time is still not fully understood. Some physicists have suggested that the arrow of time may be an emergent property of the universe's large-scale structure, rather than a fundamental feature of reality. Others propose that time may behave differently at the quantum level, where the distinction between past and future becomes blurred. This uncertainty about the nature of time is closely related to one of the biggest unresolved questions in physics: the unification of general relativity and quantum mechanics. These two foundational theories describe different aspects of the universe with extraordinary accuracy, but they are fundamentally incompatible with each other. General relativity explains the behavior of large-scale objects like stars, galaxies, and black holes, while quantum mechanics governs the behavior of particles at the smallest scales. However, when we try to apply both theories to extreme conditions, such as inside a black hole or at the moment of the Big Bang, conflicts arise, and the mathematics breaks down. A unified theory of quantum gravity, which would reconcile these two frameworks, is one of the most sought-after goals in modern physics. Several candidates for such a theory have been proposed, including string theory and loop quantum gravity, but so far, none have been experimentally confirmed. String theory, in particular, offers a tantalizing possibility for unifying all the forces of nature, including gravity, by positing that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings of energy. These strings exist in higher dimensional space, beyond the familiar 3 dimensions of space and 1 dimension of time. If string theory is correct, it could provide answers to many of the deepest mysteries of the cosmos, including the nature of black holes, the origin of the universe, and the behavior of time itself. But string theory also raises new questions, especially about the existence of extra dimensions. These hidden dimensions could be incredibly small and compactified, making them undetectable to current experiments, or they could be vast and extend beyond our observable universe. Either way, they challenge our understanding of reality and suggest that the universe may be far stranger than we ever imagined. The implications of extra dimensions, as proposed by string theory, can be mind-bending. If additional dimensions exist, they could profoundly affect the fundamental forces and particles we observe in our 4-dimensional space-time. For instance, the characteristics of gravity might be altered in these extra dimensions, potentially explaining why gravity is so much weaker than the other fundamental forces, like electromagnetism. This leads to the idea that gravity may be leaking into these hidden dimensions, which could offer insights into phenomena like dark matter and dark energy. Dark matter and dark energy represent 2 of the most significant enigmas in modern cosmology. Together, they constitute about 95% of the universe, yet we have little understanding of their true nature. Dark matter is hypothesized to account for the gravitational effects observed in galaxies and galaxy clusters, which cannot be explained solely by the visible matter we see. The rotation curves of galaxies, for instance, indicate that they should be flying apart given their visible mass, yet they remain intact, suggesting the presence of unseen mass, dark matter. Various candidates have been proposed for dark matter, ranging from weakly interacting massive particles, WIMPs, to axions and sterile neutrinos. While no direct detection of dark matter has yet occurred, numerous experiments are ongoing, searching for evidence of these elusive particles. Some scientists even speculate that dark matter may be tied to string theory and the extra dimensions, potentially allowing us to connect these disparate threads of cosmic mystery. On the other hand, dark energy is an even more perplexing phenomenon, introduced to explain the accelerated expansion of the universe. Observations of distant supernovae and the cosmic microwave background radiation indicate that not only is the universe expanding, but it is doing so at an accelerating rate. This has led to the proposal of dark energy, a mysterious force that seems to act against gravity, driving galaxies apart. The nature of dark energy remains one of the most profound mysteries in cosmology. Is it a property of space itself, as suggested by the cosmological constant introduced by Einstein? Or is it a dynamic field that changes over time? Some theories propose that dark energy could be linked to the vacuum of space or that it arises from modifications to general relativity at cosmological scales. Each of these possibilities carries its own implications for the fate of the universe. Will it continue to expand indefinitely, leading to a big freeze? Or will it eventually slow down and collapse in a big crunch? As we explore these questions, we are confronted with another fundamental mystery of the cosmos: the origins of the universe itself. The Big Bang Theory is the prevailing cosmological model that describes the universe's early development. According to this model, the universe began as an extremely hot and dense point roughly 13.8 billion years ago, and has been expanding ever since. This expansion is evidenced by the redshift of distant galaxies, which move away from us as space itself stretches. However, the Big Bang Theory raises numerous questions about what preceded the event and what might have caused it. Some theories propose that the universe could have emerged from a prior state of existence, such as a big bounce, where the universe undergoes a cyclical pattern of expansion and contraction. Others suggest the existence of a quantum foam, where the fabric of space-time is subject to quantum fluctuations, potentially giving rise to our universe from a vacuum state. Additionally, some researchers explore the possibility that our universe could be just one bubble in a vast cosmic multiverse, with each bubble representing a different universe formed through its unique Big Bang. In this scenario, our universe's properties are determined by the specific conditions of its bubble, while other bubbles may have completely different physical laws, constants, and even dimensions. The exploration of cosmic origins inevitably leads us to the question of the universe's ultimate fate. The study of cosmic evolution reveals that the future of the universe hinges on various factors, including the density of matter, the properties of dark energy, and the underlying laws of physics. Several scenarios have been proposed for the universe's fate, each with its own philosophical and existential implications. One possibility is the Big Freeze, where the universe continues to expand indefinitely, causing galaxies to drift apart and stars to burn out. In this scenario, the universe would grow increasingly dark and cold, ultimately leading to a state of heat death, where all matter is evenly distributed and no thermodynamic free energy remains to sustain processes that increase entropy. Another scenario, the Big Crunch, suggests that if the density of matter in the universe is high enough, gravitational forces could eventually slow the expansion and reverse it, leading to a collapse of the universe back into a singularity. This would mirror the conditions of the Big Bang but in reverse, posing profound questions about what happens at such extremes. There is also the potential for a Big Rip, in which the accelerated expansion caused by dark energy becomes so strong that it tears apart galaxies, stars, planets, and ultimately the very fabric of space-time itself. Each of these scenarios presents a different vision of the universe's end and invites contemplation on our existence within it. As we grapple with these cosmic mysteries, we are reminded of the fragility of our understanding. The cosmos is a vast and intricate tapestry, interwoven with enigmas that challenge our perceptions and provoke profound philosophical questions. The quest for knowledge leads us to probe deeper into the fabric of reality, from the nature of time and space to the fundamental forces that govern the universe. The exploration of these mysteries is not just an academic pursuit. It touches on the very essence of what it means to be human. Our desire to understand the cosmos reflects a deep-seated yearning to comprehend our place in the universe, to grasp the origins of existence, and to confront the inevitability of our own mortality. As we gaze up at the stars, we are reminded that the mysteries of the cosmos are not just external phenomena. They resonate within us, driving our curiosity and inspiring our imagination. In the end, the cosmos may forever elude complete understanding. Yet, it is in this very pursuit of knowledge, this quest to unravel the mysteries of the universe, that we find meaning and purpose. The questions we ask and the journeys we undertake enrich our lives, prompting us to explore the unknown, challenge our assumptions, and embrace the beauty of discovery. The cosmos, with its vastness and complexity, continues to hold countless secrets waiting to be unveiled. Each new discovery, each breakthrough in our understanding, leads to new questions and deeper mysteries, creating an endless cycle of exploration and wonder. As we stand on the brink of new frontiers in science and technology, we are poised to delve into realms of knowledge previously thought unattainable. The advancements in observational technologies, such as powerful telescopes and space-based observatories, allow us to probe deeper into the cosmos than ever before. We can observe distant galaxies, study the cosmic microwave background radiation, and investigate the effects of gravitational waves. These tools have already revolutionized our understanding of the universe, leading to groundbreaking discoveries about its origins, structure, and evolution. Moreover, the integration of artificial intelligence and machine learning into astronomical research is opening new avenues for discovery. These technologies enable researchers to analyze vast datasets, identify patterns, and make predictions about cosmic phenomena at an unprecedented scale. As we harness these advancements, we stand on the precipice of uncovering mysteries that have eluded us for centuries. The exploration of the cosmos also intersects with our philosophical and existential inquiries. As we contemplate the nature of reality, the origins of existence, and the potential for life beyond Earth, we are confronted with profound questions about consciousness, purpose, and the interconnectedness of all things. The search for extraterrestrial life, for instance, not only expands our understanding of the universe but challenges us to consider what it means to be human and our place in the grand tapestry of existence. The mysteries of the cosmos beckon us to embark on a journey of exploration, one that transcends the boundaries of science and philosophy. This journey is a collective endeavor, uniting scientists, thinkers, and dreamers across generations. Each generation adds to the tapestry of knowledge, weaving together insights and discoveries that propel us forward into the unknown. As we continue to gaze up at the stars, we are reminded that the mysteries of the cosmos are not just puzzles to be solved. They are invitations to wonder and exploration. The cosmos inspires us to embrace our curiosity, challenge our assumptions, and seek understanding in the face of uncertainty. In this quest, we discover not only the universe around us but also the depths of our own consciousness and the shared experiences that bind us as a species. In this grand adventure, we are participants in a cosmic story that is still unfolding. The mysteries of the cosmos remind us of the beauty and complexity of existence, urging us to celebrate the journey of discovery, to embrace the questions that propel us forward, and to cherish the moments of wonder that define our humanity. With every new question we ask and every mystery we uncover, we deepen our connection to the universe and to one another, forging a path toward a future rich with possibilities and untold discoveries. As we stand at the threshold of new frontiers, we must remember that the journey into the cosmos is as much about the questions we ask as it is about the answers we seek. The mysteries of the universe invite us to explore not only the physical realm but also the philosophical and existential dimensions of our existence. In this exploration, we find not only knowledge but also meaning, a profound connection to the cosmos and to each other that transcends the boundaries of space and time. With each passing day, as we continue to unravel the mysteries of the cosmos, we are reminded of the infinite possibilities that lie before us. Our quest for knowledge propels us into the unknown, igniting our imagination and fueling our dreams. The mysteries of the cosmos are not merely challenges to be solved. They are a testament to the enduring spirit of inquiry that defines humanity. In this ever-expanding universe, we remain forever curious, forever striving to understand the intricate dance of stars and galaxies, the nature of time and space, and the profound questions that resonate within our hearts. Each discovery propels us further along the path of enlightenment, revealing a universe that is not only vast but also intricately connected. As we uncover the secrets of black holes, supernovae, and the enigmatic nature of dark matter and dark energy, we are continuously reminded of our small yet significant place in this grand cosmos. Consider black holes, those cosmic monsters formed from the remnants of massive stars that have exhausted their nuclear fuel. Their gravitational pull is so intense that nothing, not even light, can escape from them. The study of black holes challenges our understanding of physics, particularly near the event horizon, the point of no return. These enigmatic objects not only warp the fabric of spacetime but also raise profound questions about the nature of reality itself. What happens to information when it falls into a black hole? This question touches on the core of quantum mechanics and general relativity, two pillars of modern physics that have yet to be reconciled. The information paradox surrounding black holes posits that information about the matter that falls into them is lost forever, contradicting the principles of quantum mechanics, which suggests that information cannot be destroyed. This paradox has prompted extensive debate and research, with various theories proposed to resolve it. Some scientists suggest that information may be preserved on the event horizon in a holographic format, while others propose that it could be released back into the universe in some form, challenging our conventional understanding of time and causality. Moreover, the existence of supermassive black holes at the centers of galaxies complicates our understanding of galactic evolution. How did these colossal entities form, and what role do they play in the development of their host galaxies? Recent observations reveal that as galaxies collide and merge, the supermassive black holes within them can also merge, resulting in a powerful release of energy and gravitational waves. These cosmic events offer tantalizing glimpses into the behavior of matter and energy under extreme conditions, providing insights into the underlying laws of physics. Beyond black holes, the study of gravitational waves, ripples in the fabric of spacetime caused by accelerating masses, has opened a new frontier in astronomy. Detected for the first time in 2015 by the LIGO Observatory, gravitational waves have provided direct evidence of the existence of binary black hole systems and neutron star mergers. This discovery has revolutionized our understanding of the universe, allowing us to observe cosmic events that were previously invisible to traditional telescopes. Gravitational wave astronomy offers a unique perspective on the universe, revealing phenomena that emit no light but exert significant influence on their surroundings. The ability to hear the universe through gravitational waves enriches our understanding of cosmic events, enabling us to probe the deepest mysteries of the cosmos, including the nature of dark matter and the potential existence of other dimensions. As we explore these cosmic wonders, we encounter the question of life beyond Earth, an inquiry that intertwines with our search for meaning in the universe. The discovery of exoplanets, planets outside our solar system, has ignited a renewed interest in the search for extraterrestrial life. With thousands of confirmed exoplanets, some located in the habitable zones of their stars, the possibility of life existing elsewhere in the universe is increasingly plausible. The quest for extraterrestrial life extends beyond mere speculation. It is grounded in the principles of astrobiology, the study of the conditions necessary for life to arise and thrive. Researchers are investigating extreme environments on Earth, such as hydrothermal vents and acidic lakes, to understand the limits of life and the potential for similar conditions to exist on other planets or moons. For instance, the icy moons of Jupiter and Saturn, Europa and Enceladus, are prime candidates in the search for extraterrestrial life due to the presence of subsurface oceans and the potential for hydrothermal activity. The question of whether we are alone in the universe has profound implications for our understanding of existence. It challenges us to reconsider our place in the cosmos and the nature of consciousness itself. If intelligent life exists elsewhere, what does that mean for our understanding of civilization, our shared responsibilities as stewards of our planet? The search for extraterrestrial intelligence, SETI, is actively monitoring the skies for signals from other civilizations, seeking to answer this fundamental question. Yet, the search for life also leads us to consider the ethical dimensions of our exploration. As we venture into the cosmos, we must grapple with the moral implications of our actions, how we interact with potential extraterrestrial ecosystems, the preservation of other worlds, and our responsibilities as an advanced species. As we forge ahead into the future, the integration of space exploration and human ingenuity will continue to reshape our understanding of the cosmos. Missions to Mars, the exploration of asteroids, and the study of other planetary bodies are expanding our knowledge of the solar system and our place within it. The prospect of human colonization of Mars raises questions about the future of our species and our ability to adapt to new environments. What challenges will we face as we venture beyond our home planet, and what ethical considerations will arise as we establish a presence on another world? Furthermore, the pursuit of knowledge in the cosmos compels us to confront our most profound existential questions. As we unravel the mysteries of the universe, we must grapple with the significance of our existence, the nature of consciousness, and the interconnectedness of all things. The cosmos is not merely a backdrop for human activity, it is an integral part of our story, shaping our beliefs, aspirations, and understanding of life itself. In contemplating the mysteries of the cosmos, we recognize that the pursuit of knowledge is a journey without end. Each discovery opens new doors, revealing layers of complexity that challenge our understanding and provoke further inquiry. As we stand on the brink of new frontiers, we are reminded that the cosmos is a vast, dynamic, and ever-evolving tapestry, inviting us to explore its depths and embrace the wonder of existence. As we move forward, let us carry the spirit of curiosity and wonder that has driven humanity throughout history. Let us celebrate the questions that propel us into the unknown and cherish the moments of discovery that illuminate our understanding of the universe. The mysteries of the cosmos are not simply puzzles to be solved. They are invitations to explore the interconnectedness of all things and to embrace the beauty of existence. With each passing day, as we continue to unravel the mysteries of the cosmos, we are reminded of the infinite possibilities that lie before us. Our quest for knowledge propels us into the unknown, igniting our imagination and fueling our dreams. The mysteries of the cosmos are not merely challenges to be solved. They are a testament to the enduring spirit of inquiry that defines humanity. As we gaze up at the night sky, let us remember that we are part of a grand cosmic narrative, woven into the fabric of the universe. The stars are not just distant points of light. They are symbols of hope and possibility, illuminating our path as we navigate the complexities of existence. In this exploration, we find not only knowledge but also meaning, a profound connection to the cosmos and to each other that transcends the boundaries of space and time. As we delve deeper into the mysteries of the cosmos, we embark on a journey that is both scientific and philosophical, challenging us to expand our horizons and redefine our understanding of reality. The cosmos beckons us to explore its wonders, to embrace the unknown, and to celebrate the beauty of discovery. In this grand adventure, we are not merely observers. We are active participants in the unfolding story of the universe, united in our quest for knowledge and understanding. And so, we continue to look to the stars, to ponder the mysteries that lie beyond our reach, and to dream of what lies ahead. The journey is far from over. It is a continuous exploration of the universe's complexities, its secrets, and its unfathomable depths. Each question leads to new discoveries, each mystery to new explorations, weaving an intricate tapestry of knowledge and understanding that binds us to the cosmos. As we embark on this endless journey, let us carry with us the lessons learned from our explorations and the wisdom gained from our inquiries. The mysteries of the cosmos remind us of the fragility of our existence and the interconnectedness of all life. They invite us to seek knowledge, to embrace curiosity, and to celebrate the beauty of the universe in all its forms. In closing, the cosmos is not merely a collection of stars and galaxies. It is a reflection of our own existence, a mirror of the questions we seek to answer and the mysteries we long to unravel. As we continue our exploration of the universe, let us remain open to the wonders that await us, and let us cherish the moments of discovery that illuminate our understanding of the cosmos and our place within it. The mysteries of the cosmos are not just challenges to be solved, they are the threads that weave together the fabric of our existence, guiding us on our journey through the vastness of space and time. As we seek answers to questions that have lingered in the minds of philosophers, scientists, and dreamers alike. What is the nature of reality? How did the universe begin, and what lies at its edge? These questions echo through the ages, resonating with our innate desire to comprehend our surroundings and the cosmos itself. The birth of the universe, often described by the Big Bang Theory, remains one of the most profound mysteries of all. Approximately 13.8 billion years ago, the universe emerged from an infinitely dense point, expanding rapidly and cooling over time to form the galaxies, stars, and planets we observe today. Yet, the precise conditions that initiated this cosmic explosion remain shrouded in mystery. What existed before the Big Bang? Was there a singularity, or was the universe part of a larger multiverse? These inquiries stretch the limits of human understanding, challenging our perceptions of time and existence. Moreover, the discovery of cosmic microwave background radiation, an afterglow from the early universe, provides a glimpse into the conditions that prevailed just moments after the Big Bang. This faint radiation, detectable from any point in the universe, serves as a relic of our cosmic origins, offering insights into the formation of structures and the evolution of the universe over billions of years. Yet, the more we learn, the more questions arise, particularly regarding the universe's fate. Will it continue to expand forever, leading to a cold, dark universe? Or will gravitational forces eventually lead to a big crunch, collapsing the universe back into a singularity? These theories illustrate the dynamic nature of cosmic exploration, where each answer leads to further inquiries. In addition to the fundamental questions of the universe's origin and fate, the nature of dark matter and dark energy presents a fascinating puzzle. Together, they constitute about 95% of the universe, yet remain elusive and largely undetectable. Dark matter, inferred from its gravitational effects on visible matter, appears to be a mysterious substance that does not interact with light, rendering it invisible. The ongoing quest to identify the particles that constitute dark matter fuels research in particle physics and cosmology, as scientists attempt to unveil the hidden aspects of our universe. Dark energy, on the other hand, represents a force driving the accelerated expansion of the universe. This enigmatic energy, which seems to counteract gravitational attraction, poses profound questions about the nature of space and time. What is dark energy, and what role does it play in the ultimate fate of the universe? As researchers develop increasingly sophisticated observational techniques and technologies, the pursuit of answers to these questions becomes more critical than ever. The exploration of the cosmos is not solely confined to the distant universe. It also extends to our own solar system, where tantalizing mysteries abound. The ongoing study of celestial bodies, planets, moons, asteroids, and comets, provides insights into the history of our solar system and the potential for life beyond Earth. For instance, the recent exploration of Mars has unveiled evidence of past water, indicating that the planet may have once harbored conditions suitable for life. As missions like NASA's Perseverance rover continue to search for signs of ancient microbial life, our understanding of life's potential beyond Earth deepens. Moreover, the study of the outer solar system reveals intriguing possibilities for habitability. The icy moons of Jupiter and Saturn, such as Europa and Enceladus, possess subsurface oceans beneath their icy crusts, creating environments where life may thrive. These moons are prime targets for future exploration, as they may harbor the conditions necessary for life, offering a unique glimpse into the possibilities of existence beyond our planet. Astrobiology, the study of life's potential in the universe, embodies our desire to explore these possibilities. By examining extreme environments on Earth, scientists gain insights into the resilience of life and its potential to survive in harsh conditions. From hydrothermal vents on the ocean floor to acidic lakes and frozen tundras, life demonstrates remarkable adaptability, suggesting that similar conditions may exist elsewhere in the cosmos. The search for extraterrestrial life not only fuels scientific inquiry but also poses profound philosophical questions. If we were to discover life beyond Earth, how would it reshape our understanding of existence? Would it affirm our uniqueness or challenge our notions of intelligence and consciousness? These questions compel us to reflect on our values, our role as stewards of our planet, and the ethical implications of our search for life beyond Earth. As we gaze into the cosmos, we are also confronted with the vastness of time. The universe is approximately 13.8 billion years old, and its history is marked by cataclysmic events, such as supernovae and gamma-ray bursts, that have shaped its evolution. Each cosmic event leaves an indelible mark, contributing to the dynamic interplay of matter and energy that defines our universe. The remnants of these events, including neutron stars and black holes, serve as cosmic signposts, illuminating the processes that govern the evolution of galaxies and the birth of new stars. In this exploration, the study of stellar life cycles reveals the intricate dance of creation and destruction. Stars are born from the collapse of gas and dust, undergoing nuclear fusion to produce light and heat. As they exhaust their nuclear fuel, they undergo dramatic transformations, culminating in spectacular explosions known as supernovae. These explosive events scatter elements throughout the universe, enriching the cosmic environment and providing the building blocks for new stars, planets, and potentially life itself. The life cycle of stars is intimately connected to the broader narrative of the universe, illustrating the interconnectedness of all matter. The very elements that constitute our bodies, carbon, nitrogen, oxygen, were forged in the hearts of ancient stars, reminding us of our cosmic origins. This realization prompts us to reflect on our place within the universe and the shared heritage that unites all living beings. As we delve deeper into the mysteries of the cosmos, we are reminded of the importance of collaboration and inquiry. The International Space Station, ISS, serves as a testament to this collaborative spirit, bringing together scientists and astronauts from around the world to conduct research in microgravity. The discoveries made aboard the ISS not only advance our understanding of fundamental physics and biology, but also reinforce the notion that our shared goals extend beyond our individual pursuits. The advancement of technology has played a pivotal role in expanding our understanding of the cosmos. From powerful telescopes that capture the light from distant galaxies to sophisticated spacecraft that traverse the solar system, technology has opened new frontiers in exploration. The Hubble Space Telescope, launched in 1990, has provided breathtaking images of the universe, revealing cosmic phenomena previously hidden from view. Its observations have led to groundbreaking discoveries, including the acceleration of the universe's expansion and the identification of exoplanets. Looking ahead, the next generation of telescopes and space missions promises to unlock even more mysteries of the cosmos. The James Webb Space Telescope, set to launch in the near future, aims to delve deeper into the universe's history, providing unprecedented insights into the formation of stars and galaxies, as well as the conditions for life on distant exoplanets. These advancements inspire hope and excitement, fueling our curiosity and our desire to explore the unknown. The mysteries of the cosmos invite us to reflect on our own existence and the stories we share as a species. As we contemplate the vastness of space, we are reminded of our common humanity, our shared dreams, and our aspirations for a better future. As we stand on the brink of discovery, we are filled with a sense of wonder and anticipation. The cosmos beckons us to explore, to question, and to embrace the unknown. Each moment of discovery brings us closer to unraveling the mysteries that have captivated humanity for millennia. Our exploration of the universe is not merely a scientific endeavor, it is a deeply human pursuit, one that reflects our desire to understand our place in the cosmos and to connect with something greater than ourselves. In the grand tapestry of the universe, every star, every galaxy, and every celestial phenomenon plays a role in shaping our understanding of existence. The mysteries of the cosmos remind us that we are part of a larger narrative, a story that spans eons and transcends time. As we continue our journey through the stars, let us embrace the unknown, celebrate the beauty of discovery, and cherish the moments that illuminate our understanding of the universe and our place within it. The cosmos is a boundless expanse of wonder, a realm of infinite possibilities that invites us to explore, to question, and to dream. It is a reminder that our journey is far from over. It is an ongoing adventure filled with mystery and discovery. Each inquiry, each revelation, and each cosmic event serves as a stepping stone toward a deeper understanding of the universe and our role in it. As we look to the future, let us remain committed to our quest for knowledge and understanding. The mysteries of the cosmos are not simply puzzles to be solved. They are gateways to new realms of inquiry and exploration. They inspire us to push the boundaries of our understanding and to embrace the complexities of existence. The universe is a canvas of wonder, inviting us to paint our own stories within its vastness. With each discovery, we weave a thread into the fabric of our cosmic narrative, creating a tapestry that reflects our shared dreams and aspirations. As we venture forth into the unknown, let us carry with us the spirit of curiosity, the courage to question, and the resolve to explore. In this journey of discovery, we are united by our shared humanity and our collective quest for understanding. The mysteries of the cosmos remind us of the beauty and complexity of existence, urging us to embrace the unknown and to celebrate the moments of wonder that illuminate our path. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.